So this is the second exam, which we term the midterm. The first one is the quiz. And it was given in March 2024, about a month away from the end of lectures and covering the first part of rigid body kinematics. So the goals here were really to cover particle kinetics, which we had completed particle kinetics with work energy, momentum, second law, and start to talk a little bit about rigid body kinematics. So the first question is, a small block B of mass 6 kilos is sliding down a straight section of a frictionless ramp angled at 25 degrees as shown in the diagram. Block B is linked to the origin by a spring of stiffness K equals 30 newtons per meter. At the instant shown in the diagram, B has a speed of 2.8 meters per second, and the spring is stretched by 0.32 meters beyond its relaxed length. So you're first asked to determine the angular momentum of the block about that point of origin. And so ROB is perpendicular to VB. So HO, which we can calculate from this from a scalar approach, is just going to be mass times velocity of B times the distance from the mass B to the center of rotation. So 0.3 meters divided by sine of 25, you can see that in the diagram, 6 kilos, 2.8 meters per second in the K direction. You could also do this as a vector approach, and it's R cross MVB, and you just have to recognize that ROBX equals ROBY divided by tan of theta, and so you put both of the terms in, cross multiply it by the components of velocity. And no surprises here. Either way, you would get the same result, 11.9 kilogram meter squared per second in the K direction. If you had a problem with your positive directions, you would get a negative value on your vector solution. So both approaches are valid, both equal value of 5 marks for this approach. And you can see how we sort of distributed those results. Determine the time rate of change of angular momentum of block B at the instant shown in the diagram. Express your coordinate in the X, Y, Z coordinate system. So again, you have the wall, you have the spring force, and you have the weight. Now, both the wall force and the spring force are acting normal to the spring, or parallel to the spring. The only thing that is acting in any direction relative to the spring is the weight. And gravity is, again, 9.81 meters per second squared. So you could do sum of moments, because that's the definition of time rate of change of angular momentum. And if you remember that from the lectures, R cross F. Determine these examine the free body diagram of block B. The only force is the component of weight that is acting perpendicular to the radial distance O to B. So put all the terms in, 0.3 divided by sine 25, all of that together. You can do the same thing, but recognize that weight causes the moment. You've got to break it up into its component directions, ROBX, ROBY. All other forces are parallel, go to 0. And so in terms of time rate of change of angular momentum, both approaches, again, equal value and 5 marks for the approach. So time rate of change of angular momentum, 37.9 kilogram meter squared second squared K. Units matter, by the way. I shouldn't sort of ignore that point. Remember that it is not a valid solution unless you also write units. So at the last part, you're given the spring stretch at position B and position D. You're then given the height relative to the top and the velocity. Now, you could do whatever you wanted with the height. You could define it at the bottom. You could do it however you want to. I did it this way. It's just easier. Velocity at the beginning, 2.8 meters per second. And your only unknown is the final velocity of the system. Solve for that. So I do it with work energy. Put every term in. The term in red, V2 squared, of course, is the unknown. All of the other terms are known. Those are in your table above. And you get a final velocity of 4.34 meters per second. Again, point breakdown here in terms of what we expected. So we're covering sections 3.6, 3.7. You can also write this in terms of work energy. And the reason why I'm saying this is because I got a lot of questions during the term. How are work energy and conserved forces, conservative form of the kinetic and potential energy forms the same or different? And they're the exact same equation. If you write them correctly, you will get the same result as you see with the V2 equal equation that is the second from the bottom of this. So it slides down the ramp onto the horizontal surface, impacts the stationary block D, which has a mass of 2.5 kilos. When the blocks collide, they stick together and move together in the positive x direction. What percentage of kinetic energy is lost from the system of two blocks in the collision? So before collision and after collision, you have the two things. You can find out, you don't have to solve for anything. You can just say mass of B, VB, and then the combined mass of the system times its final velocity of BD, and both of those have to equal each other for conservation of linear momentum to be true. And you end up with a velocity of BD, which is 3.8 or 3.06 meters per second. You can examine the kinetic energy at that point, and you can calculate all the terms out, VB squared over VBD squared, or VBD squared over VB. And that's 0.71, or a loss of 29.4%. There's no need to actually calculate those velocities. Those velocities are irrelevant. You really just want the final ratio between the two velocities. So from that, either approach is fine. Both will sort of work out the same way, and you get 3.9, 3.6, 3.7 for the text sections that you wanted. Now, this is probably the more complex part of the problem. You have a linkage, which consists of an arm OA, a link AB, and B is constrained to move horizontally, left and right. You have LOA, which is 4 meters, LOAB, which is 3 meters. The motion of point B in the slotted groove is controlled by the rotation of link OA. For the instant shown, the angular velocity of OA is given as 0.5 rads per second K. Velocity, you're asked to find velocity of point A and XY, angular velocity and velocity of point B in an XYZ coordinates. So velocity of point A, you can sort of do graphics here. You put down velocity of A equals 4 omega minus cos theta sine beta j. Put in theta, calculate all the terms. Beta equals 90 minus theta. But really, I don't know why you would. I would do it with the vector solution, which are shown at the right. Same thing. All the terms are there. You just look at the geometry. You get the same result. Minus 1.2i plus 1.6j meters per second. And the magnitude of that velocity at that point is 2 meters per second. So both approaches are valid. I think that the more straightforward, least complex geometrically is the one on the right. So section 5. Now, for the angular velocity B, velocity of point B in XY coordinates, XYZ coordinates. So you want omega AB and VB. You have velocity of A equals velocity B plus VA relative to B. VA relative to B is omega AB cross RAB. You can do all of the calculations. And again, I'm doing this as a vector solution here. You could do it geometrically. And substituting all the terms that I have, and you end up with velocity of A, which is given as minus 2.4 omega AB plus VBI minus 1.8 omega ABJ. And from this, you have enough information to solve everything. You have I and J components, and from those I and J components, you solve for omega AB, which is minus 0.89 K, and rads per second, and velocity of B, which is minus 3.33 meters per second in the I direction. And remember, that kind of makes sense because velocity of B is constrained to move in the slider. And again, here's sort of the diagram of all of that. You can do it geometrically. You can use sort of a graphical approach and solve through for everything. But again, as you're doing these things, I really recommend you try it both ways and convince yourself what is the easiest way to solve these kind of complex motions. And this is a very complex motion if you think about it. Section 5.4 from the text, and everything's working. So the vector approach is there, all of the terms, and same thing, you get sort of the same result out of it. So either way will work, but you can see this is a lot easier. And it's a lot easier because you're just looking at the geometry of the motion. You're not, or geometry of the physical positions, not the geometry of the motion, which is often more difficult to visualize. Sort of section 5.4 of the text, and all of that's there. Final question, this turned out to be kind of difficult. Knowing the coefficient of kinetic friction between mass of B and the ground is mu k equals 0.3, MA, both of the masses are 3 kilograms. Assume the blocks are sliding, and this covers sections 293233. So it's a free body diagram. As usual, you want to write everything, but the first thing you do is the constrained motion. So you know that 2ya plus xb plus constants equal constant. So from that, taking the derivatives, you find that 2va plus vb equals 0, 2aa plus ab equals 0. And I haven't put any signs on anything here. And it's really important to understand this type of approach is really looking at the rate of change of length. And so it's going to tell me that VA, or the rate of change of the length of A, is the negative rate of change of the length of B. So in other words, if I stretch A by a meter downward, then A is going to increase in length and B is going to decrease by 2 meters. So acceleration of A in terms of magnitude is half of acceleration of B, or acceleration of B equals twice acceleration of A. So all terms there you go. Half mark for having 2 FBDs, there you go. Those are the free body diagrams. Sum of forces in Y equals mass times acceleration of A, mg minus 2t equals mass times acceleration of A. So acceleration of A equals g minus 2t over m. Sum of forces in y, mg equals n. Sum of forces in x, mab, mu k n minus t equals mab. You don't have a lot of work to do once you've written out the equations of motion. Substitute all the terms in, everything works out. You have from n what in the top equation, and you end up with equation 3, acceleration v equals mu k g minus t over m. So substitute all the terms in, sections 3.2 to 3.4. Substitute that into the equations to acceleration a plus acceleration b, so put all the terms there. Substitute everything, and I'm kind of assuming everything's going positive. And then I will get from this that tension in the cable is 13.5 newtons. Substitute into my acceleration A term, I get 0.08 g, and acceleration of A is downwards 0.7848 meters per second squared. Acceleration B, put the terms in, I get everything, get rid of the mass. Then I get 1.57 meters per second squared. And it makes sense. If A is moving downwards, I expect B to move to the left. So those all work out really well. Now, this is going to be important, and it's something I put into the syllabus on an annual basis, and I kind of encourage you to read it. But this quiz can't cover everything in this dynamic concept inventory. What it does do is say that different points on a rigid body have different velocities, but we don't test you on accelerations. And that was question 2. Angular velocities are property of the body as a whole and can vary with time. Question 2. In general, total mechanical energy is not conserved during an impact. Question 1. And I've marked on here all of the sort of corresponding lectures for all of the rest of the material. In terms of conclusions, remember the dynamic concept inventory, angular momentum, particle kinetics, and rigid body kinematics, which is going to come out at the end. Velocity is really all we are really talking about right now, but you'll see with the final exam, we also expect you to know